This video is on section 7.9 and 7.10. So we're going to start with section 7.9 on the Dirac delta function, and it will be written as delta of t. The Dirac delta function is characterized by the following two properties. It is equal to this piecewise function, where it's equal to 0 at any time that t is not equal to 0. But when t is equal to 0, it's equal to infinity. And also, the integral of a function multiplied by the delta function from negative infinity to positive infinity is just equal to that function at 0, as long as that function is continuous on an open interval containing t equals 0. You may notice immediately this isn't really a function because of this fact that it can take on infinity at a point. So we're going to relax our definition of a function for this section as we move on, because we will find this to be quite useful. So the first thing we'll look at is, what is delta of t minus a? So can I translate the delta function? And yes, I can. We will get that delta of t minus a is equal to 0 whenever t is not equal to a, and that the integral from negative infinity to positive infinity of any function that's continuous around a multiplied by delta t minus a is not equal to f of 0, but equal to f of a. This 4 shouldn't be here, it's a typo. And that's true for any function that is continuous on an open interval containing t equals not 0, it's a, because a is now the center of this delta function. Since the Dirac delta function is not a function in the usual sense, we will give it a new name. We'll call it a generalized function or a distribution. That's a little more appropriate than calling it a function. To imagine the usefulness of this function, imagine a sudden strike like a hammer. The transfer of momentum from hammer to nail takes place over a very short time, but is very large. So you can kind of picture that if the hammer doesn't strike the nail until time a, then there's nothing happening on either side of a, but at a, it's a very high point, and we essentially just say it's infinity. But you can see page 406 to get more of an explanation of the theory behind the Dirac delta function. But for now, we'll move on. Let's find the Laplacian transform of the Dirac delta function centered at a. So we have this, the integral from negative infinity of any function multiplied by the Dirac delta function is equal to f of 0, or in this case, f of a. But our Laplacian actually looks a lot like that. It's an integral from 0 to infinity of e to the negative st times our function in question. Now, the one thing we need to square is the difference between this integral and this integral. The integral from negative infinity to positive infinity, and the integral from 0 to positive infinity. Well, something very important is noted here. For this to be true, a must be greater than 0. So if we look back at the picture here, if a is greater than 0, and I calculate the integral from negative infinity to positive infinity of this Dirac delta function, well, it's 0 everywhere. If I'm calculating the integral of some sort of bound that doesn't contain this a point, then the area under the curve is clearly 0. But if I'm counting any bound that includes the a point, then I'm going to get the entire integral. The integral from negative infinity is going to be the same as the integral from here to here, because the only thing that's important is catching the area underneath this infinite term a. So since a is greater than 0, calculating the integral from negative infinity to infinity is the same as calculating the integral from 0 to infinity. So these are interchangeable in this instance because of the properties of the Dirac delta function. So since that is true, then the Dirac delta function says f of a is going to be our solution here. So if I take e to the negative st and I replace t with a, I get e to the negative as my f of a term. So that is the Laplacian transform of the Dirac delta function. It is equal to e to the negative as, and we'll make use of that moving forward. Here's another property of the Dirac delta function. If we just let our function in question f equal 1, then we're only multiplying the delta function by 1, and f of 0 is just equal to 1, because f of anything is equal to 1. So this gives us the property that the integral from negative infinity to positive infinity of the delta function is just equal to 1. What happens if we try to calculate with f equal to the unit step function? Well, the Dirac delta function says that I just plug in a for t, and I get the unit step function of 0. The unit step function at 0 is actually not defined, because the unit step function is equal to 1 when t is greater than 0, and 0 when t is less than 0, but it's not actually defined at 0. So we get this value is not defined, and we can immediately see why, because we didn't follow the rules. The unit step function is not continuous on an open interval containing 0. The unit step function looks like this, with a jump discontinuity right there at 0. So that's why you can't calculate the Dirac delta function integral here, where you're calculating f using the unit step function. But now, as for what we can use for this unit step function, we're going to find that out with our next example. So if t is less than a, and we kind of went over this already, then the integral from negative infinity to t of the Dirac delta function of x minus a is just 0. So looking back at what this graph would mean, if I wanted the integral from negative infinity all the way up to t, but a is somewhere over here, and remember, a is the point where we have that high infinite value. Well, everything else is 0. This entire integral, I'm just calculating the area underneath a curve that is at 0, so it's 0. So you're not really calculating anything when you calculate that integral. It's just a horizontal line at y equals 0, so its integral is 0. However, what about the more interesting case where t is greater than a? What if I'm calculating the integral all the way up to t here and say a is within there? What is actually the area under that curve when the only point that is above 0 is way up at infinity? Well, this integral is equal to the integral from negative infinity to positive infinity of the delta function t minus a. Because as we said, if you're calculating any integral that contains that point a, then you might as well calculate the whole thing, because everything else is zeros. But we have an identity for what this is equal to. We just calculated it up here. So these are the same thing. Now, what was the point of this? What have we shown? Well, we can conclude that the integral of the delta function, delta t minus a, is actually the unit step function u of t minus a. Because up until this point a, the integral is equal to 0. But as soon as we calculate the integral of any area including a, then it's equal to 1. In the same way that the unit step function is 0 until you reach a, and then it's 1. Making use of this, we're going to move to the first example. Solve the symbolic initial value problem. The second derivative of y with respect to t plus 2y is equal to 4 times the Dirac delta function centered at 1, or t minus 1. And we have the initial value y of 0 equals 2. And the derivative of y with respect to t at 0 is equal to 0. We use the word symbolic. We say symbolic initial value problem because delta is not a function under the traditional definition. So to even put delta into an equation is a little bit of an issue. So again, we're noting that this doesn't follow all of our rigorous rules of mathematics, but we can find use for this theoretical function whose integral is the unit step function. So let's take the Laplacian of both sides, and we'll simplify things by just calling the Laplacian of y capital Y. So we've done this enough times. We know that this Laplacian of y double prime comes down as all 3 of these pieces. s squared times the Laplacian of y minus y of 0 times s minus y prime of 0. Laplacian of 2y just simplifies as 2 times capital Y. Now, what is the Laplacian of 4 times the delta function centered at 1? Well, let's go back up and check when we calculated what our Laplacian is of the delta function. It's just e to the negative as, where a is this value right here. So that means it is e to the negative 1 times s, and this 4 that was a factor is just going to come down. Now, factoring out the capital Y from all the common terms, we get s squared plus 2 times y. This 2s right here is going to get added to both sides. And then we're going to divide both sides by s squared plus 2 so we can isolate capital Y. So we have capital Y, which remember is the Laplacian of little y, is equal to 4e to the negative s plus 2s divided by s squared plus 2. Now we can break that sum up. So we get e to the negative s times 4 over s squared plus 2, added to 2 times s over s squared plus 2. Now we've done problems like this before, so you're probably noticing that we're getting this form of something squared over s squared plus something else squared. So we need to take this form because we know these are the Laplacians of sine and cos. In particular, sine is going to be the one that has the same value here and here, and cos is going to be the one that has the s on the top as its only real difference. So the important thing to note is we need the top and the bottom to match, and the bottom needs to be something squared. Well, our denominator has s squared plus 2. 2 isn't really a perfect square, but it is root 2 squared. So our value of interest is going to be root 2. The problem is 4 is not equal to root 2. So we're going to need to factor out this 2 times root 2 to leave root 2 in the numerator. Now we have it in the proper form though. We have our b value, which is root 2, divided by s squared plus b squared. So that's going to give us, that is the Laplacian of sine bt, and b is root 2. This one works a little better for us because s is in the numerator, and that's exactly what we want in the numerator when we're dealing with the Laplacian of cos. But we do need to express the denominator as a square plus another square. So this 2 comes down as root 2 squared. And that ends up being the Laplacian of cos bt, where b is equal to root 2. Now, we're going to take the inverse Laplace of both sides of this equation so that we can turn capital Y back into little y. Remember, our substitution was to make capital Y equal to the Laplacian of y. So let's take the inverse Laplace of both sides of this equation. Well, this is going to be incredibly simple. The inverse Laplace of the Laplace of something, they're just going to cancel. So we get 2 cos root 2t. There gets to be a bit of an issue with this second part here because we have a product. We have this e to the negative s on the outside multiplied by our Laplace of sine root t. We're going to use one of our rules from 7.6, and that is that the Laplacian inverse of e to the negative as times f of s is equal to f of t minus a times u of t minus a. Now, if you'll recall, this capital S is the Laplacian of little s. So our form is the Laplacian inverse of e to the negative 1s times the Laplacian of sine root 2t. To put that in this form, we are going to do this. So we get that f of t minus a is root sine of root 2 t minus 1, because a is equal to 1 in this instance, the factor in this power. And we're going to multiply that by u of t minus a. And remember, a is equal to 1, so it's just u of t minus 1. So that's the identity we've used to move from this to this. Now that is a final answer, but if you would like to write this as a piecewise function, you would note that when you multiply something by u of t minus 1, that essentially says it is going to be 0 until you reach the value 1. So until you get to 1, for any t value less than 1, this whole bit here is just multiplied by 0. So it doesn't exist. So we just have this 2 cos root 2t. But as soon as t is greater than 1, then the unit step function says instead of multiplying by 1, you're going to multiply by, instead of multiplying by 0, you're going to multiply by 1. So suddenly this bit exists. And this is how you can view this as a piecewise function. Now that is the end of section 2.9. Section 2.10 is very short, and that's why I've included it in this video as well. And it's really just one example. It's going to tie together a lot of what we've learned from this chapter, and we're going to be able to solve linear equations using Laplace transforms. So we're going to try to find solutions for y and x given this system of equations and these initial values. So 2x prime plus y is equal to 6 times t, and y prime plus 3x plus x prime is equal to 2t minus 5. And we're given initial values. X of 0 is equal to 3, and y of 0 is equal to -2. Okay, we're going to take the Laplacian of both sides of both equations. And we've got 2 equations on the go here, so I'm going to try to keep these labeled for you. So equation 1, we take the Laplacian of both sides. We do the same thing to equation 2. We're now going to try to simplify this because there's going to be a lot of variables running around. So let's try to get these Laplaces out of the way. So we're going to let the Laplacian of little y equal capital Y, and we're going to let the Laplacian of little x equal capital X. So equation 1 becomes 2 times Sx minus 3. Now think about what we're doing there. The Laplacian of 2x prime is equal to 2 times the Laplacian of x prime. And remember, the Laplacian of x prime, we're just going to get that that is 2 times the Laplacian of x minus x0. We already know that x0 is 3. So that's how we're getting that this is 2 times Sx minus 3, because the Laplacian of little x we're just writing as capital X. The Laplacian of y is just capital Y, so that's simple enough. And we can calculate the Laplacian of 6t. We know that either from memory or from the back of the book at this point. It's just 6 over s squared. So this is still working with equation 1. We're just simplifying here. We get 2 times Sx plus y, and we're going to multiply this 2 by -3 to give us -6 is equal to 6 over s squared. And this is our equation, the way we're going to leave it for now. So now we're going to work with equation 2. Well, y prime is going to follow the same rules as x prime. So it's going to become sy minus y of 0, which is -2. So that minus will become a plus for us. Plus 3 times capital X, plus we've got another x prime here. So we need to do the same calculation as before. That's Sx minus 3. And the right side of this equation can also be calculated at this point, because we know the Laplacian of 2t and we know the Laplacian of 5. So we get 2 over s squared minus 5 over s. We'll continue simplifying equation 2 here. So we get sy plus 2 minus 3. So that's where this minus 1 comes from. We're adding 2, but we're subtracting 3. And we're getting 3 plus s times x. So those are our two equations, 1 and 2. They've been simplified slightly by using our Laplace. Now we're going to use elimination to eliminate this capital Y term and calculate for capital X. So we're going to take equation 2 and subtract equation 1. And on the right, we're doing the same thing. Equation 2 minus equation 1. So now the reason we've done that, sy minus sy is just going to cancel. And we'll get a common denominator on the right, simplify as best we can. And we're trying to isolate this x term. So we're just moving this negative 1 plus 6s over to the right side. Getting a common denominator. And then we're going to divide both sides by 3 plus s minus 2x minus 2s squared. So this is our solution for what capital X is equal to. But remember, we're not really interested in what the Laplacian of x is, which is this capital X. We want to know what the original function x is. So we need to find a way to take the inverse Laplace of this whole thing. Well, that's going to be partial fractions. So we're going to take this form. I did one step here where I simplified it and broke it up into smaller pieces. And that gives you an idea of how it looks and how some of these things can cancel out. Notice here how that 11s canceled out with one of these s squareds in the denominator. But if you're actually going to do partial fractions, it's quicker to do it all at once instead of trying to break it into 3 separate chunks. So this may be interesting, but we're going to jump down to here. So this is going to be equal to a over s plus b over s squared plus cs plus d over this non-reducible polynomial, negative 2s squared plus s plus 3. Well, you can forget about the denominators. Multiply a by s times negative 2s squared plus s plus 3. B is just going to get multiplied by negative 2s squared plus s plus 3. And cs plus d is just going to be multiplied by s squared. Now, when we multiply that through, we're going to do the same thing we always do, where we're going to take our s cubed coefficients and set them equal to each other. So we have negative 6 is equal to negative 2a plus c. Then we'll do the same thing with our s squared coefficients. Positive 1 is going to be equal to a minus 2b plus d. Our s coefficient, minus 11, is going to be equal to 3a plus b. And finally, our constant, 2, is going to be equal to 3b. Now, I always find this to be a lot of fun. Maybe it's not your cup of tea. But first thing we're going to do, b doesn't have any other variables involved, so we can make that 2/3. But then that means I can just plug in 2/3 into this equation. So now a is the only variable here. So I can get a solution for a as being negative 35 over 9. Well, c is written in terms of a, so that means c can now be solved for. Let's see what happens there. C is equal to 2a minus 6. So c is equal to 2 times negative 35 over 9 minus 6. C is equal to negative 70 over 9 minus 54 over 9. So C is equal to negative 124 over 9. I suppose for completeness, I should also show how A was solved for. Negative 11 is equal to 3A plus 2/3. So this is negative 33 over 3, that's your negative 11, minus 2 over 3 is equal to 3a. That gives us negative 35 over 3 divided by 3 is negative 35 over 9 is equal to A. And now finally, I can plug in my A, my B, and my C is not necessary, just my A and my B. So negative 35 over 9, 2 times B. And that's going to give me D is equal to 56 over 9. Because if 1 is equal to negative 35 over 9 minus 4 over 3 plus D, that means D is equal to 1 plus 35 over 9 plus 12 over 9. And remember, 1 is just 9 over 9. So that's going to give us 9 plus 35 plus 12 is 56. We plug these A, B, C, and D values in. A, B, C, and D. And now we need to calculate these inverse Laplaces. Well, the inverse Laplace of 1 over S is just 1. So negative 35 over 9 times 1 over S, when you take the inverse Laplace, is just negative 35 over 9. The inverse Laplace of 1 over S squared is T. So 2/3 times 1 over S squared becomes 2/3 T. Here's where things are going to get a little bit more tricky. This S over negative 2S squared plus S plus 3. This is looking a little bit, but not much, like our old cosine signs that we take the inverse Laplaces of. So the first thing we're going to do is multiply by negative 2, because that is going to get rid of that S squared in the, it's going to keep the S squared, but it's going to get rid of the negative 2 in the denominator there, because we want the coefficient on the S squared term to be 1. So if I multiply the numerator and the denominator by negative 2, we're going to factor out negative 2. That's it. So when we factor out negative 2 from this denominator, it's just going to divide through by that 124, and that's how we end up with positive 62 as opposed to negative 124. Perfect. We're going to do the same thing here. So positive 56 is going to become negative 28 because we want that S squared to have a 1 coefficient in front of it. So everything here stays the same. We've already calculated these things, but we're still working inside these brackets. So we have S over S minus 1 over 4 squared. So how did we do that? Remember that at the back of our book, we have things that look like S over S squared plus B squared, or S over S squared minus B squared. But there's nothing that looks like S over S squared plus BS plus B squared. Like this S term here, it's just not there. It needs to be gotten rid of. Well, the only way we're going to get rid of it is to complete the square here. So what is 1/2 of this? It's negative 1 over 4. So that becomes the square we're interested in, S minus 1 over 4 squared. So what is S minus 1 over 4 squared? That is S squared minus 1/2 S plus 1 over 16. So I'm adding 1 over 16, but that means I need to subtract 1 over 16 as well. So negative 3 over 2 minus 1 over 16 is equal to negative 24 over 16 minus 1 over 16 is equal to negative 25 over 16. So that's how negative 25 over 16 is this value here. Now, we're still not done, because if we look at this form here, s over s squared minus b squared, well, right now I have it in the form of s over s minus 1 over 4 squared minus b squared. The problem is s and s minus 1 over 4 are not the same thing. So I need to turn the numerator into s minus 1 over 4. So I will subtract 1 over 4 and add 1 over 4. Notice how in the denominator I now have a square here, because actually 25 over 16, that's just 5 over 4 squared, because it's a square over a square. So that worked out simply enough. Over here, the numerator isn't s. It's actually just a number. So what do we do in that instance? Well, this isn't taking the form of s over s squared minus b squared. This is taking the form of b over s squared minus b squared, which again is something we're familiar with from the Laplace table at the back of the book. But the important thing here is these b values must be the same. So my numerator has to be 5 over 4. Problem is the numerator is 1. So I'm going to need to both multiply and divide by 5 over 4. So that means I get my 5 over 4 in the numerator, but I have to bring a 4 over 5 out front as a coefficient. Now that all those steps have been completed, I have everything I need here to get the hyperbolic cosine of 5 over 4t, actually e to the 1 over 4 times the hyperbolic cosine of 5 over 4t. Because I have s minus 1 over 4 over s minus 1 over 4 squared minus 5 over 4 squared. So we get this e to the 1 over 4t because we've translated it by 1 over 4. We get the hyperbolic cosine from the back of the book as being the form s over s squared minus b squared. And we get the 5 over 4 because that's our b value. That's the value being squared. The problem is I have this extra 1 over 4 in the numerator. I can't forget about that. So that comes down here. We're also ready to solve this one. We have 5 over 4 in the numerator, 5 over 4 squared in the denominator, and s minus 1 over 4 squared as our s term. So this is e to the 1 over 4. Again, the 1 over 4 representing that translation. Hyperbolic sign comes from the back of the book. And 5 over 4 is our b value. And this takes the form of b over s squared minus b squared. And that's your hyperbolic sign Laplace. So we're getting there. We just have one last one to work with. Well, this looks very similar to what we just did with the hyperbolic sign. But we have 1 over 4 in the numerator when we need 5 over 4 in the numerator. So we're going to need to multiply and divide by 5. And that's how this 9 in the denominator becomes a 45, because we've multiplied by 5 here. So we have to divide by 5 to cancel it out. So now this just becomes the same thing we just solved for, honestly, e to the 1 over 4 sine 5 over 4t. Well, we have like terms that can now be combined. So this does simplify a lot better than it looked like it was going to. This just becomes negative 50 over 45, which is just negative 10 over 9. We're going to further simplify, though, because hyperbolic sine and hyperbolic cos can be rewritten. The hyperbolic cosine is e to the 5 over 4t, because it's 5 over 4t, plus e to the negative 5 over 4t divided by 2. So that's your hyperbolic cosine of 5 over 4t. Well, if I multiply my e to the 1 over 4t by that, I'm just going to add 1 over 4 to both of these powers, and that's going to give me e to the 3 over 2t plus e to the negative t. What about this 2 going on out here? Well, I'm just going to divide it, so this 62 becomes 31. Now I'm going to do something similar over here with hyperbolic sine, because hyperbolic sine takes the form e to the 5 over 4t minus e to the negative 5/4t divided by 2. Well, again, we're just going to divide by 2 out here. So instead of 10/9, it's now 5/9. And when we multiply by e to the 1/4, it's going to become e to the 3/2t minus e to the negative t. Now, that's our solution for x. You may be scared at this point that we have to go through the process all over again just to solve for y. Plug this in, get y. But that's a nice trick about this is once you know what x is, we have one of our original equations stated that 2x prime plus y is equal to 6t. So if I can just figure out what 2x prime is, then I'll know what y is. Well, I know what x is, and I know how to take a derivative. So let's take that derivative and multiply it by 2. And that's going to give me, this becomes 0 because there's no t term. This becomes 2/3, which multiplies by 2 to give me 4/3. 31/9 e to the 3/2t. Well, when you do a derivative of e, all you're going to do is really just chain rule to bring this 3/2 down. But then we have to multiply it by 2 because we're calculating 2 times x prime. So you can check yourself how all these terms come about by just taking the derivative and then multiplying it by 2. And then by isolating y, we get this final answer where it's equal to 2x prime that should be a plus 6t. Tripped over the last hurdle. And that's our final answer for y. So when we want to solve this system of equations, our solution is this is y and this is x.